Why are there so many strange looking letters and symbols in physics? In math, we had X, Y, and Z, or Z. Those were the variables. In chemistry, we had uppercase letters with subscripts and superscripts. Those are the elements. But now in physics, the letters look even stranger. What do they all mean? Well, my name's Deidre Hamaguchi. I'm a professional fighter and I'm also a professional physics teacher, so I'm going to break this down for you. Let's divide these physics symbols into 3 groups. The first group are the letters that have either an arrow above them or they don't have an arrow above them. The second group are letters with small numbers below or above. We call those subscripts if they're below and superscripts if they're above. The third group of letters are all the Greek letters, which look like the letters that they use in sorority and fraternity names. So let's talk about the first group, which is letters with the arrows. The arrows above a letter mean that that variable is what we call a vector quantity. On the other hand, if the letter does not have an arrow above it, then it is what we call a scalar quantity. Okay, so now we got to define what that means. A vector is a quantity that has a size and a direction. So for example, the first ones you'll encounter are velocity, lowercase v with the arrow, acceleration, lowercase a with the arrow, and force, uppercase F with the arrow. Now examples of scalars, on the other hand, are mass, lowercase m, and time, lowercase t. Now I suppose you could argue that time moves forward, so it does have a direction, but I suppose since we can only go forward in time, we can't go backwards, and we'll just consider it a scalar for our purposes. Now, this is probably the first time that you're asked to think about scalars versus vectors, because up until this point in life, we've only dealt with things that we would consider scalars, so why would we bother defining a vector? We didn't really need to. So this is a new distinction, and it's something that you do need to wrap your head around, because the scalar versus vector categorization goes throughout the whole entire physics course. Every single physics quantity you learn about will be either a scalar or a vector. It cannot be both, and it must be one. It cannot be neither a vector or a scalar. So the reason it's important for you to know whether something's a vector or a scalar is not only so you can get that question right on a multiple choice question asking you to identify whether it's a scalar or vector, but much more importantly, if you know that something's a vector, that gives you a big clue on how you're going to solve the problem. Because if it's a scalar, we can just mostly treat things as we would numbers in math and quote unquote do the math. If something's a vector, you have to probably draw a diagram to make sure you're keeping your direction straight, because the direction is indicated by either a positive or a negative sign, and the direction can also involve you doing a little bit of trig like sine and cos, and then the Pythagorean theorem perhaps to calculate the length of a hypotenuse. So in other words, problem solving with vector quantities can be much more involved than dealing with scalar quantities, and that is a very critical clue for you to know how to solve the problem. The second group of symbols, what are those little numbers below and above? Well, remember, it's different than chemistry for physics. Okay, in chemistry, all the subscripts told us how many of that atom there are in a molecule. So, as you know, H2O means there's 2 hydrogens and 1 oxygen in a water molecule. CO2 means there's 1 carbon molecule, or 1 carbon atom and 2 oxygen atoms in a carbon dioxide molecule. But the subscripts in physics do not mean that there's 2 of that thing. So, for example, lowercase m sub 1 means simply mass 1, and lowercase m sub 2 means mass 2. We're just using the 1s and 2s to distinguish one mass from the other. Similarly, v arrow sub 1 would mean the velocity of that mass 1. V arrow sub 2 would mean the velocity of that mass 2. The subscripts, you could think of them as adjectives. Now, you may also see letters used instead of numbers, so it could be m sub A, m sub B, v sub A, v sub B, meaning mass A, mass B, velocity of mass A, velocity of mass B, respectively. You may also see parts of words or a word as a subscript to a physics variable. So, for example, you could see V arrow subscript AVG, which would stand for the average velocity. Now, you should know another way to symbolize average velocity. Physicists use what we call V bar. So instead of having the arrow above the V, we just have a little straight line, hence V bar. V bar means average velocity. Other subscripts you might see are TOT, which stands for total, and NET, which stands for net. Those we'll come back to when I talk about the third category, but they both mean this. They all mean the same thing. So net means net as in your net earnings, as opposed to your gross earnings. Your net earnings. It does not mean it means you would take your gross earnings and subtract the deductions to find your net earnings. So that would be considered like your total earnings, because that's what you're taking home. Okay, now I'll come back to that when we talk about the third type of symbol, the Greek letters. But let's move on to the small numbers that you see above the letter. We call those superscripts. And in physics, they are just like they are in math. The superscripts in physics are exponents, so you should do the math. So, for example, first formula you learned in constant acceleration, delta x equals v0 delta t plus 1/2 a arrow delta t squared. The superscript 2 by the second delta t term means multiply delta t times itself. Okay, so we can think about the superscripts in physics being just like math, not chemistry. Okay, finally, the Greek letters in physics. Okay, now one I just mentioned with the T, delta T. Delta looks like a triangle, and it's the uppercase Greek letter D. Okay, in physics and in math, that delta means, quote, the change in blank, end quote, whatever it is next to. So, for example, delta T means the change in time. Delta KE means the change in kinetic energy. Now, here's a key thing that's really crucial. Delta always means take the final minus the initial. Take the final time, subtract the initial time. Take the final kinetic energy and subtract the initial kinetic energy. This is a really common error I find a lot of physics students make, is they flip that around and do initial minus final, but it's the opposite of that. So don't fall into that trap for yourself. Now, the second Greek letter you'll see probably is what we call sigma, and it looks like a kind of pointy uppercase E. Sigma means, quote, the sum of blank, end quote. So the sum of whatever the sigma is next to. So for example, Newton's second law, we have sigma, uppercase F, arrow, equals mass m times acceleration a, arrow. Okay, so the sigma F means the sum of the forces. And just to reiterate, some physics instructors and some physics textbooks will use the uppercase F arrow subscript net or subscript TOT. Others will use the sigma capital F. So they all mean exactly the same thing. That you have to add up the force vectors and set that equal to the mass times its acceleration. And of course, since it's force is a vector, you may need to apply your geometry to arrive at your final answer. Okay, the key here is that the letters delta and sigma are not separate variables, even though they're letters. Okay, so you're in math, whenever there's one letter and another letter right next to each other, you multiply them together. But with delta and sigma, they're not numbers. They're more like a verb. They're instructions. Find the sum of this. Find the change in this. Now, in addition to those two uppercase letters, there are also some lowercase Greek letters that do have numerical values. For example, probably the first one you'll encounter is called mu, and it looks like a lowercase u with a little tail at the beginning, but it's actually a lowercase Greek m. And mu stands, in most cases, for a coefficient. The one you'll likely use is the coefficient of friction. Now, a coefficient does have a numeric value, so you'll either be asked to solve for it or you'll be given that value to find something else to plug into a formula. A second Greek letter you'll definitely use in physics is called lambda, and it looks like it's the Greek letter for a lowercase l. And if you write in Chinese or Japanese, it looks like a mirror image of the character for person. And lambda stands for wavelength, which is, as the name implies, the length of one full cycle of a wave. So in summary, the arrows over a letter tell you if it's a vector. So be mindful of directions and geometry if you're dealing with any vector quantities, because you may need to use trig. The subscripts under the letter are like adjectives. The superscripts above the letter are exponents, so just do the math. The Greek letters delta and sigma tell you what to do, whereas the lower cases mu and lambda stand for a number that you will either solve for or plug in. Now, as with all new languages, to get fluent, you have to practice. And it does take a little bit of time, but over time, you'll find yourself getting more and more comfortable with using these symbols. So I hope I was able to explain that to help you get started with your course. If you have any questions, please put them in the comments. And as always, please like, comment, and share. Thank you.